So, good morning. Today, we're going to look at something called expected value. Now, today's stuff is going to involve a lot of common sense in that outcomes are a lot of times going to be exactly what you thought they should be. Let me give you a really simple example. If I take a fair coin and I flip the coin, we know it's half, going to be heads, half going to be tails. Well, but if I flip the coin 2 million times, does that mean I'm going to get exactly 1 million heads and 1 million tails? Because actually the probability of any particular outcome is not particularly high. But it sure seems reasonable that if I flip a coin over and over and over and over again, we should see about half the number of heads and about half the number of tails. Well, mathematically speaking, we can actually prove that we should expect half. Now, that's expect half. That doesn't mean that's what we're going to get. That just means it's the most likely. So if I roll the dice, for example, and I said, well, what should I expect as a total? I can get 2 through 12, and I have probabilities for each of these. Well, it turns out, think of it kind of like an average. The average is kind of what I should expect. So the idea with expected value is you can calculate ahead of time if you know the probabilities of outcomes. So here's the way we're going to do this. And again, if you've had statistics, this should feel very familiar. So we start usually with a capital X, and we call this a random variable. And the funny thing is it's neither random and it's not really a variable, but that's the term we use. It's called a random variable. What it is, it's all the possible outcomes of any experiment. Okay, so the individual outcomes. So X would be a set of things, little x's. This is a big X. X1, X2, let's say up to Xn. Let's say there are n possible outcomes. So this could be something like roll the dice and add them up. So the possible outcomes would be totals of 2, 3, 4, 5, 6, up to 12. Those would be my little x's. So if each of these has an associated probability, let's say that little pi is the probability that my random variable takes on the value of little xi. This is the formal mathematical notation. The probability that the random variable is equal to this value, we sometimes just abbreviate it and say the probability of that individual outcome, and we'll call it little pi. So each of these outcomes has an associated probability. These are little p's. Okay. So I know that if I roll the dice, I already know what the probabilities of each outcome are. So therefore, if I want to know, then what is the most likely outcome? That's called the expected value. And we use the following notation. The expected value of capital X, we call it capital E of X. Expected value of X is X1 P1 plus X2 P2 plus all the way to Xn Pn, or in other words, the sum from I equal 1 to n of Xi Pi. This is the formal definition of expected value of any experiment. I take the probability of each outcome and I simply add them up. Okay, it's really not all that complicated. And the great part is the results not only should always make perfect sense, but often it's the case where you'd say, oh, that's exactly what I was expecting it to be. That just seems like the most likely outcome. So let's do a simple example. Let's think about rolling the dice, okay? So I'm going to roll the dice. This is my experiment. Roll the dice and find the total. Okay, then let X be, you always define a random variable. Let X equal the total on the dice. Or the total of the dice, probably a better way of saying it. Then the possible values that X can take on. In fact, let me do it in table form. This is the way we did it originally. So I have a total, okay, So the random variable will be the total. The total was 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. These were my possible totals. We know that. We know the probability was 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36, 5 over 36, 4 over 36, 3 over 36, 2 over 36, 1 over 36. I'm going to roll the dice one time. What should I expect the total to be? That doesn't mean that's what it is. It just means it's the most likely outcome. So in this case, the expected value of X is 2 times 1 over 36 plus 3 times 2 over 36. I'll write it like this, just kind of save some time. This product plus this product plus this product plus this product. So if I get out my calculator and I multiply all these together, let's take a moment. Everyone do this on your own for a moment. Now, here's what I do. I'm lazy. Since every denominator is 36, just multiply the numerators, add it up, and divide by 36. It's a little bit faster. So 2 times 1 plus 3 times 2 plus 4 times 3, all the way down the line, all over 36. Tell me when you have an answer, anybody. It's not that long, but there are 11 calculations involved. So I have 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12, all over 36. So holler out when you get a number here. Anyone? Is anybody actually there? I'll stop recording. I'll wait. So the expected value is 7. Now, if I'm looking at my dice roll chart and I rolled the dice, 7 was the highest outcome, but then 6 and 8 had the same probability. 5 and 9 have the same probability, and so on. So if I just said, well, what is the most likely outcome? It's kind of like the average. Wasn't the average 7? Yeah, but not only the highest probability, but the average of my rolls was 7. So mathematically, we calculate the expected is 7. Now, what does that mean exactly? Here's the easiest way to think of expected value. If I perform the same experiment repeatedly, okay, over and over and over and over again, I am likely to see the expected value more than anything else. Okay, it doesn't mean I'm going to get it every time. So an easy way to think about this is, let's think of coin flips, because coin flips are so easy to understand. If I flip a coin 2 times, does that mean I'm going to get 1 head and 1 tail? Am I going to get 1 head and 1 tail if I flip a coin 2 times? Think about that.
No, nothing's guaranteed.
Yeah, I could get 2 heads, I could get 2 tails, but wouldn't you say it's the most likely result? So here's what I would do. By the way, if I was teaching stats, we would actually do this in class. I'd say, all right, everyone take out a coin and I want you to flip it 10 times because that will only take you a minute. And I want you to write down the number of tails you get. So one person's going to get 6, another person's going to get 7, another one's going to get 3, somebody's going to get 5, all. But if I said, now for the entire class, let's find the average number of tails we got for the entire class, because now you're talking several hundred coin flips. You know what you're going to see? You're going to see really darn close, because everybody did it 10 times. You're going to see a number really close to 5. Probably never going to see exactly 5, but you might see 4.9 or 5.03 or something. When you do the same experiment over and over again, when the probabilities are known, you tend to see the outcomes you expect. There's actually a name for this in mathematics, believe it or not. It's called the law of large numbers. Now, doesn't that sound made up? The law of large numbers. It actually means when the probabilities are known ahead of time and you do the same thing over and over and over again, what you should see is exactly what you should expect. So if I do flip a coin 1,000,000 times, I should see about half of the results head and about half the results tails. It's not necessarily going to be exactly that. Okay, so can you apply this to other areas in life in general? Yeah, oh yeah. In fact, all investing works this way. All insurance works this way because if there's money involved, they want to get it right. Everything, absolutely everything when it comes to money is based on expected values, expected returns, things like that, because certain probabilities are known ahead of time, and therefore we can make conclusions. So this is a very simple example. Let's do a coin flip now. Keep this really simple. I don't want this to get too complicated. So let's say we're going to flip a coin, and I'm going to make it somewhat complicated. Let's say flip a coin 3 times. Okay, it's a fair coin. We're going to flip 3 times. So we want to count the number of tails. Now, if I flip a coin 3 times, I can get no tails, I can get 1 tail, I can get 2 tails, I can get 3 tails. Now, we've done this before. This was a problem that you already did. We did it with 4 coin flips a couple quizzes ago. So let's first write down all the possible outcomes, okay? I can do heads, 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 tails. Heads, tails, heads, heads, tails, tails. Tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. These are the outcomes, and we know each of these are equally likely. Each of these outcomes has a probability of exactly 1/8. So now let's define our random variable. These are not what I'm going to count. I'm going to count the number of tails. So let's let our random variable x equal the number of tails. Therefore, what values can x take on? Exactly. Anybody? I'm flipping the coin 3 times. Exactly what values can x take on?
Heads and tails.
0, 1, 2, and 3.
0, 1, 2, or 3. Yeah, x has to be a value. It can't be it can't be anything other than a number because I'm going to be multiplying. Now, let's just make our life easy. Let's write the probability under. Now, what is 0 tails? That's this guy right here. Okay, you agree? That's 0 tails. So it has a probability of 1/8. 1 tail. That happens here, here, and here. Agreed? So what's the probability of 1 tail? Anybody? The probability of
3/8.
3/8. All right. 2 tails. Let's see. 2 tails would be here, here, here. So also 3/8. And 3 tails would be that guy right there, 1/8. And really quick check. Yes, my probabilities add up to 1. That's a good thing, by the way. If I didn't add up to 1, that meant I was missing something or I double counted something. All right. So I'm going to flip a coin 3 times. Mathematically, how many tails should I expect? So the expected value of x equals 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Anybody want? Let's do this real quickly. So 3/8 plus 6/8, that's 9/8 plus 12/8, that's exactly 1.5. If I flip a coin 3 times, I should expect exactly 1.5 tails. In other words, exactly half my outcomes. Oh, but that's not an achievable. No, it isn't. But here's what I want you to do. I want everybody in the class to flip a coin 3 times. So we're going to see all 3 of these outcomes. And if I said, let's take the average for the entire class, guess what the average is going to be? Something really close to 1.5. Now, this is called a binomial experiment. We talked about this one yesterday. A binomial experiment is one that has exactly 2 outcomes. So, but I had several outcomes. No. I'm flipping a coin. I can get a head or I can get a tail. Oh, okay. So in this case here, because we're counting tails, we would call tails a success. We would call heads a failure. So this is 0 successes, 1 success, 2 success, 3 successes. And what is my expected number of successes? Would be 1.5 if I flipped a coin 3 times. So what if I flipped a coin 10 times and I did the exact same problem and I did 0 through 10 and all of the individual probabilities? That would take us a lot longer, by the way, because the individual probabilities would probably be a little bit harder, but we could do it. Does anybody want to guess what would we probably see for expected value if we flipped the same coin 10 times?
1.5.
10 times.
Be 5.
5.
5.
Do we know this? Yes. I'm not going to do the formal proof of this. This formal proof is usually in higher level textbooks because it's a little bit complicated and it involves stuff that we haven't really covered in this class. But the formal proof is this. Excuse me. Okay. In a binomial experiment, with probability, spell this correctly, of success, we usually use little p, and I mentioned yesterday, we usually use little p for success and little q for failure, and then p plus q have to add up to 1. In a binomial experiment with the probability of success p and n trials. Now, what's a trial? It's how many times I do it. So in this case here, this is my n. I did this 3 times. In the dice rolling problem, n was 1. I only rolled the dice 1 time. So the number of trials, if I said, okay, a moment ago I asked you, what about 10 coin flips? That would be 10 trials. What makes something a binomial experiment is a couple of different things. One is the probability of success is known ahead of time. This isn't random. This isn't something that has to be calculated down the road. I already know the probability of success and I know the number of trials. If you've had statistics, you know the answer to this. Does anyone know what? There's actually a simple formula for this. In a binomial experiment, the expected value is, does anybody know? Just holler it out if you think you know.
P over N.
It's P, N trials.
P over N or N
times P. That's an absolute mathematical law. Oh, so if I flip the coin 10 times and the probability of success is 0.5, I should get 0.5 times 10 tails. That's it. It's actually that simple. But that's only in a binomial experiment. Most experiments aren't binomial experiments, right? I rolled the dice a moment ago and we said we had totals from 2 through 12. That's 11 different outcomes. That's not binomial. Okay. Oh, can I make it binomial? Yeah, you had an outcome of 7 or
not 7.
Not 7. Good. That's how you make a binomial. But then, figuring out probabilities might be a little more complicated. So expected value is simply take the outcome and multiply it by its probability. And when you add them all up. Now, we're going to do several examples of this just to make it easier to understand. Okay. Now, one of the simplest ways to understand this, believe it or not, is something like a raffle. Now, a raffle is usually some means of making money for some charitable organization, right? They're selling raffle tickets at a certain cost. Then later they're going to have a draw for the prizes, and let's say the prizes are money and lots of money is going to be paid out, but probably not the same amount of money as they took in. Okay, that kind of defeats the whole point. So if they take in $1 million, they might be giving out $500,000 in prizes because the whole point of the raffle was to raise money. But is it possible that I give away all the money, or worse, is it possible that I actually give away more money than I took in? I suppose. So let's suppose we have the following raffle, all right? Let's keep it real simple. 1,000 tickets are sold at $1,000 each. This is a very expensive raffle, okay? There is one first prize of $500,000. Whoa. There are 2 second prizes of $100,000. There are 10 third prizes of $10,000. And there are going to be, let's say, 50 fourth prizes of how about $5,000. So there's a lot of people that are going to win, and there's a lot of people that are going to win a lot of money. Okay, now you bought a raffle ticket, or basically anybody who bought a raffle ticket. What is the expected return? Now, what I mean by expected return is you start, you're where you are, but now you're going to spend $1,000. Well, if you win money, obviously you're going to end up positive. If you don't win anything, you're out $1,000. Okay, so what can you expect as the final outcome at the end of this? Well, then let's figure out, when you walk in, you're paying your $1,000. So even if, let's say you win $5,000, are you $5,000 ahead if you win $5,000? So do you walk away $5,000 richer if you win $5,000?
No, it's $4,000
$4,000. Why?
because you paid $1,000.
Because you had to spend $1,000. Oh, okay. Yeah, you don't get your, by the way, when you buy a raffle ticket, you don't get the money back and then a prize. No. You bought the raffle ticket for the opportunity to win the prize. Oh, so there's going to be a lot of people that come out of this at negative $1,000, aren't they? Because most people aren't going to win anything. So let's let X equal the possible outcomes. Okay. So then X would equal, well, if I win $500,000, then what is actually my outcome? It's not $500,000. It's what?
4,000.
400,000?
499,000.
Probably 499. Yeah, it's only $1,000.
Yeah,
$499,000. Or if I win 100,000, it's really $99,000. Or if I win 10,000, it's really 9,000 kids. I had to buy the ticket. If I win 5,000, it's really 4,000. And these are all dollars. These do have units. And there's one more outcome.
Negative 1,000.
Negative 1,000. Yeah, if I don't include that one, I'm not going to get a very meaningful answer. Now, what are the probabilities of each of these outcomes? 1,000 tickets are sold. There is one first prize. So what's the probability? 1 out of 1,000. How about the next one? 2. Okay, and the next one? 10. And the next one? 50. What's the last one? Is it 1,000 out of 1,000?
It'd be 1,000 minus 63.
Oh, how many prizes have we given out so far? We've given out 63 prizes. So how many people are left? That would be what, 937? Okay. Why? Well, first of all, these probabilities have to add up to 1. If they don't add up to 1, we got a problem. So it's 1 out of 1,000 people are going to win this, 2 out of 1,000, and so on. 937 out of 1,000 are going to lose $1,000. So now when I'm computing expected value, this times this plus, this times this plus, this times this, all the way down the line. Now, if you want to be lazy, the easiest way to do it is just do the numerators and then take your total over 1,000. I mean, that's faster that way. So let's go ahead and figure this out. So 499. All right. Anybody got a number? I got a number.
Is it 613.996? Although I could have definitely just done it wrong.
Yeah, it's actually a nice happy round number.
Yeah, I did it wrong.
Being that everything's in thousands, you probably
Never mind.
50,000?
50,000? You forgot to divide by 1,000. Is it 50,000?
Yeah, that's my bad. I didn't divide by 1,000.
Is it positive or is it negative? Keep going. So what's this answer exactly? You're on the right track, Sabrina.
Oh, it's 50,000 divided by 1,000. Right?
So
It'd be $50.
So what does this mean in simple English? First of all, this is the most generous raffle ever because they just lost a lot of money. That means the average person, of everybody who bought the raffle ticket, the average is to come out of this $50 richer. But if you're one of the 937, you're saying, I didn't come out richer. No, but if you're any of these guys, you're saying, yeah. So the idea is each person who buys a raffle ticket is either going to win or lose something. But the expected value, the expected return, which would be the same as saying the overall average of every single person who bought a raffle ticket, is positive $50. Now, the reason this would be a lousy raffle is the people holding the raffle just lost money. So usually with a raffle, the expected value would be negative. So what if I change one aspect of this raffle? I'm a bored rich guy, so I don't mind this. But let's just say I'm an individual who just likes messing around with the numbers. And I'm going to change one thing about this. Let's do that. Let me change one thing. I'm going to make this $75,000 instead of $100,000. I'm going to change this. So that means that this will now be 74,000. What will that do to my final answer?
Make it smaller.
Well,
It'll make it 0.
We'll make it 0. That's interesting. That means nobody made money, nobody lost money. It's a total break even. I wonder if that's significant. Yeah. When the expected value is 0, we call this a fair game. That's actually a mathematical term. In any scenario where there's gains and losses, and the easiest way to think about it is always think about it in terms of money. And if you were a gambler, it would always be money. But it might be that I'm doing an investment. It might be that my work is such that I could make money or I could lose money at my job, depending on certain events. If the expected value or the expected return is 0, then we say the whole process is a fair game. Nobody has an advantage. So if I had a raffle where the expected return is 0, another way of thinking about that is I gave away every penny that came in. Not one penny more, not one penny less, but everything was given out. Now, if you were a gambler, and you're going to Las Vegas, you're going to some casino and you were a gambler, how many fair games do you suppose there are at a casino? How many games of chance is the expected return 0? Want to take a shot at that one? None.
They're probably below 0 by a bit, right?
Every game of chance at every casino has a negative expected return. Why logically does that make sense to you?
So the
The casino was to make money.
Yeah, it's a business.
It's a business, or at the very least, they want to be able to stay open. Why? Because if, let's just say at every casino, the expected return was 0, that they give away exactly the amount of money that came in, as the fairest casino on planet Earth, why wouldn't they last very long?
They're literally losing money.
Couldn't pay their
Losing
bill.
money because
They didn't make any
that?
profit.
what's above you? What's over your head?
Couldn't keep the lights on.
Your overhead. You can't keep the lights on. Exactly. In other words, you have costs. You got to pay your rent. You got to pay your employees. You got to pay for all those free drinks you're giving away at midnight, to get people to keep gambling. A casino has to make money or they can't stay open. So the expected return at a casino is always they're always going to make money. That doesn't make them cruel and evil. It's bad business if you're running a business and you don't make any money. That's just not a very good business because you have your overhead, you have your costs. Okay, so games of chance at a casino, the casino has to win the majority of time. Now, is it overwhelming? Not necessarily, but they have to win the majority of time or there's no point in playing the game. So let's suppose you and your friend want to play a game, right? You're not a casino, just the two of you. And we're going to keep it a simple game here. we're gonna roll a die, a single die. Okay, we're gonna roll the die one time. Okay, now here's how it works. Now think of it in terms of you, not your friend. In other words, what's the expected return for you? So if the die is a 1, a 2, or a 6, you win $10. If the die is a 3 or a 5, you pay $8. If the die is a 4, you pay $12. So here's my question. Okay, we want to make it a little bit interesting. All right, so it doesn't matter who rolls the die. If the die, I roll the die, it lands a 2. Great, you're going to give me $10. I roll the die, it lands a 4. I'm going to give you $12. We're just going to do it once. Now, the thing is, we could repeat this game over and over and over again, but that doesn't change the expected value. The expected return is going to be the same no matter how many times I do this. So we only need to do it one time. So if we're talking in terms of me, what is my expected return? Now, how can we figure that out, folks? You didn't have to pay to get into this game. We're just going to be handing money back and forth. So if X is the possible outcomes for me, what are the possible outcomes, by the way, for me?
10, -8, and -12.
And -8 and -12. And these are all dollars. Very important to realize, those are negative because I'm paying out. Now, what are the probabilities? What's the probability of 10?
1/2.
It's 1/36.
1/6. Or 3/6.
Yeah, 3/6. How about this one?
2/6.
And this one?
1/6.
By the way, is it correct to say 1/2, 1/3, 1/6? Is that correct?
Yes.
Is it a good idea?
Probably not.
No. By the way, every single person who reduces their fractions on the probabilities is doing good mathematics and usually gets the wrong answer. Because now you've got to add a series of sums and products all with different denominators, and that makes everything more complicated. Now, the easiest way to do this is leave all your denominators the same. You can always reduce the final answer, but if I reduce my probabilities as I go, then when I combine terms, there's arithmetic errors just waiting to happen in that case. All right, so what is the expected return? Well, let's see. It'd be 10 times 3/6 plus -8 times 2/6 plus -12 times 1/6. And what does this come out exactly? Again, since it's all over 6, it's easy to just add numerators.
2/6.
It's 2/6. So the expected return is basically $0.33 because this is dollars, by the way. So what does that mean? Well, it's not 0. Is this a fair game? Yes or no?
No.
No.
No, this is not a fair game. In fact, is this a game you should play?
Yes.
Yes, over and over and over again. Play as long as you can play this game. Why? Because your expected return is positive. Does it mean you're going to win every time?
No.
No, it means in the long run, you should have won more than you lost. Now, there's something called the gambler's folly. Has anybody ever heard that expression? The gambler's folly. It's a class. This goes back hundreds of years. You see, I've known people to make mistakes when they gambled. They made emotional decisions or different things. The gambler's folly is the idea that I've lost a bunch in a row, maybe. Well, I have to win at some point. My luck has to turn around. At some point, the dice have to go my way or something to that effect. No, actually, it doesn't. there's two parts to the gambler's folly. One is the idea that you're going to win back your money. Well, the money didn't know it belonged to you. Every time you play, it starts over. But the other thing is, if you do anything that has a negative expected return, and you do this over a long period of time, you should lose rather than gain. Now, is it possible you could win? Is it still possible you could win? Yeah, I mean, when people play a slot machine, they put in the nickel and they pull the thing and they won $1,000. Great. That's possible. But the majority of people who play are losing. Why? Because if they weren't losing, then the casino's not making any money. If everybody's winning, they would go broke really fast. So the idea is, if the expected return is negative, you're not going to win in the long run, but can you still win in the short run? Yes. Now, mathematically, I've seen the proof of this. Is actually not that complicated. Mathematically, if you want to maximize your winnings, and you can think calculus in this sense, if I want to maximize my winnings and or minimize my losses. You're a gambler, you're going to play. Don't say, well, just don't play. No. You're going to play. You're going to play a game with a negative expected return. Now, this game you should play over and over and over again because it's positive. But you're going to play a game of chance with a negative expected return. But you want to maximize your winnings or minimize your losses. Mathematically speaking, then how many times should you play that game?
0.
No, I said you're going to play. No matter what, you're going to play. You don't have a choice. You're going to play. Did you guys ever see Deer Hunter? You're going to play that game of roulette. You don't get a choice. One time. You can prove mathematically one time. If you win, you walk away. Why? Because if the expected return is negative, then over the long period, you should expect to lose money. But if you win on your first try, you've maximized your winnings. If you lose on your first try, walk away. Then you've minimized your losses because, again, over the long term. But I could still win on my 10th try or my 20th. Yes, you can. But from a mathematical and probability standpoint, it's not very likely. Okay, because the numbers don't lie in this case. So the idea is, if I want to maximize my winnings or minimize my losses and I'm going to play, you play one time. That's fine. But if, let's say, you want to play over and over again, that's okay. But understand that if the expected return is negative, then you actually shouldn't expect to win in the long run. You can. Now, I've got all sorts of interesting stories that I'll tell you guys later that I've seen personally happen. And in some cases they were good, in some cases they weren't so good, of people making decisions, while they were gambling, and not always a good decision. So the idea here is, a fair game is when this is 0. So here's what I want to do. I want to keep playing with my friend, but my friend doesn't want to play because I win most of the time. Well, that's not a very fun game. So here's what we're going to do. We're going to adjust our game. My orange here. We're going to adjust our game. I need to change something about my game so that my friend will continue to play with me. In other words, I want to make this a fair game. But I don't want to start from scratch and reinvent everything. I want to change one thing. So everybody think about this for a moment. You're going to change one thing and one thing only. Anybody got an idea?
I have a couple of ideas.
Yeah, give me one of them.
You can change the pay to 8 to 9.
So this 8 here, you're saying change this to 9. Okay, what would happen if I change that to 9? Then that would be -9. That would be -9. And my answer would be, in fact, 0. Does anybody else have a different change? That's perfect. Is there a different change in here somewhere?
Well, technically, you can change the payouts to anything that.
But you're only going to change one thing, though.
Right.
If you're only going to change one thing, and it wasn't this.
12 to a 14.
12 to a 14. That would also have worked. You probably don't want to mess with this one because then you'd have thirds and it gets kind of icky. You probably don't want to mess with these guys because now you're starting all over. But something as simple as changing one of the payouts to make this be 0. So a lot of times the question will be asked, okay, here we're going to do this. So what should the last scenario be in order to make it a fair game? And now you'd have to actually calculate it. So I'm giving you an extremely simple example. So expected value is also how people do investments. You say, what do you mean? Let's say you're a weekend investor. You know, you're one of those people that go online and you're doing all of your own stuff. You don't use a broker. That's a lot of people do that now, but you do a little bit of research. I mean, you're paying attention to things and you're saying, hey, this particular investment is going to make a lot of money if things go well, or it's going to lose a lot of money if things don't go well. Okay, that's kind of a typical scenario. But what's the probability things go well? What's the probability things don't go well? Okay. I knew somebody who was a contractor and they lived in Seattle. Now, you're a contractor, you're building things. You live in Seattle. What would be an issue with that, by the way, when you're trying to build things? You're building houses, you're building structures, and you live in Seattle. What do you have to deal with? Anybody?
Rain.
Rain. And the one thing, by the way, I am the only male in my family who's not a contractor. My brothers, my father, my brother-in-law, they're all contractors. They've been contractors for years. So I know a little bit about the industry. I mean, I've been in many job sites. And the one thing you cannot do, you can't work in the rain. Nope, you can't pour cement in the rain. You can't do framing in the rain. You can't like do a new roof in the rain. Rain kind of messes things up. So you're a contractor and you're trying to figure out, you know, your schedule for the week. You have to take into account what is the probability it's going to rain. So let's do a really simple example and we'll keep it really, really simple. All right. Now I got to pay, I still have to pay employees perhaps, or I still have to pay for certain things, certain overhead. All right. So let's say if we work, we make tomorrow, let's say if we work, we make $10,000. If we don't work, we lose, let's say $2,000 because there's certain fixed costs. You know, I'm renting equipment. You know, I got also, but the $10,000 is how much profit we're going to make. Okay, taking into account everything else. $2,000 means I lost some money. I had to pay bills but I never got to work. And we cannot work in the rain. Okay, we cannot work in the rain. Tomorrow, there is an 80% chance of rain. Okay. How much money should I expect to make or lose tomorrow? That's the question. By the way, this is an everyday real life type of scenario. Oh, if I work, I make money. If I don't work, I lose money. And both of them have probabilities that are not zero. Now, if we were talking about, you know, you're out in the middle of the desert, you know, it's probably not going to rain tomorrow. But you're in Seattle, it's probably going to rain tomorrow. So first of all, what are my possible outcomes?
$10,000 or -2.
$10,000, -2. That's it. What are my probabilities? By the way, you don't use percentage as probability. You use percentage when you're speaking in the English language. So when I've had people say, the probability is 80%. No, 80% is not a probability. Probability is 0.8. Well, isn't it the same thing? 80 and 0.8 are not the same thing. 80% means 80 over 100. But nobody writes a decimal when they say percent. Never use percentage when you're saying probability. If there's an 80% chance of rain, which means the probability of rain is 80? No, 0.8. Okay, so the 80% chance of rain means the probability I'm going to lose $2,000 is 0.8. So what's the probability it will not rain?
2 out of 10. 0.2.
0.2. So now, based on all of this, and let's say this may be a daily thing. So in a 5-day week, if it's 80% chance of rain every day, then I can kind of expect it's going to rain 4 out of the 5 days. That's actually reasonable. Might rain all 5, might not rain any of them. So my expected return, or my expected value in this case, is 10,000 times 0.2 plus -2,000. Sorry, that's the dollar sign. Can't write today. Times 0.8. And what is this value exactly? Anybody?
$400.
$400, but it's positive. So it's sort of like this. Somebody has presented me with this opportunity. I haven't decided yet. They said, hey, if you work and do this job, you're going to get $10,000, but you've got to bring in all your own equipment. So you got to rent, the thing that mixes the cement, and you got to, rent the dumpster, and you got to do all the stuff. But you guys can make $10,000. But there's an 80% chance of rain. Now I'm the contractor. Should I take this job? This is not an easy question. Should I take this job?
Yes.
On the surface, it seems obvious. But what if I'm struggling? What if I'm really having a difficult time making ends meet? There's a really high probability. There's a really high probability that I'm going to lose money, and maybe I can't afford it. So really the rule of thumb is there's a positive expected return. If this was literally the case every single day, for let's say every day for the next month, they've said, hey, we want you to do this job. Maybe this job is I'm building an entire condominium complex. There's work for many, 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 many days. Yeah, because on the average, I'll make $400 a day. So that takes into account all the days I couldn't work, but then days I could work. But if this was a one-shot deal, really the rule of thumb is, can you afford to lose the $2,000? Oh, so remember the raffle example? We had a positive expected return of $50. So shouldn't that mean automatically you buy the raffle ticket? No. What if you can't afford the $1,000 it costs to buy the ticket? Then you shouldn't buy the raffle ticket. But if buying the raffle ticket isn't really a dent, it doesn't hurt you to spend that $1,000. Yes, then you should play that raffle all the time, because in the long run, you're going to average winning $50 every time you play. Okay, so if I played that raffle 100 days in a row, I should find that I averaged $50 a day. But if I can't afford the $1,000 raffle ticket and I don't win in the first few tries, that's hurting me. So a lot of times business decisions are not made strictly on that number, but also, can I afford that in the long run? Okay, so that's kind of thing. So in investments in general, every investment will have a built-in probability. Now, the probabilities are not set in stone because things change on a daily basis. And that's why people, who are money managers, they do well financially, because they're making decisions, and every decision is expected value. Now, what about insurance? If anybody here has life insurance, I'm curious, just say out loud, does anyone here have life insurance? Because I'm not looking at the screen. You have a policy?
Some sort of
policy. So I'll let you know how it works. By the way, the younger you buy life insurance, the cheaper it's going to be, for the simple reason that you're going to live longer. The later in life you buy life insurance, the more expensive it's going to be, because you're not going to live as long. No one knows when you're going to die, but they know in 20 years you have 20 less years to live. So it's all based on the probability you live another day or another year. Now, when you do life insurance, let's say you're going to get life insurance for the first time. Well, the first thing is somebody's usually going to come to your home. Now, I don't know how that worked during the pandemic, but they're going to do things like take your vitals, take your blood pressure, probably do a blood test, do all these things to make sure that you do not have a terminal disease. And they're not going to, you can't buy life insurance if you have a terminal disease. It's that simple. No one's going to, sell you life insurance and then give you the $1 million if you die in a few months or something. That's not how it works. So you have to first prove that you're healthy. Now, they'll ask a whole series of questionnaires of your lifestyle. Are you a smoker? Are you a drinker? Do you ride a motorcycle? That's actually one of the top ones. Why would they ask you those types of questions? Well, if you said yes to any of those, that means the probability of dying from one of those is much higher. I'm not a smoker, so the probability of me dying of lung cancer is extremely low. I don't ride a motorcycle, so the probability of me being killed in a motorcycle accident, it's pretty low. But if I love, one of my hobbies is to skydive. That's a joke. But if you have dangerous habits, your life insurance is going to be much more expensive, because the probability that you don't survive is much higher. So all life insurance is based on this. They're called actuarial tables, and there's a whole branch. There's jobs where that's all you do, is that it's the probability that you'll live another day, basically. Now, this is kind of from tomorrow's lecture. We're going to be doing what's called conditional probability, which is how this is done. Okay. But the idea is if all insurances, by the way, auto insurance, if you have a history of accidents and tickets, then the probability that you're going to get into another accident or have a ticket is much higher than if you don't. So the expected outcome of you driving is probably not as good. So the insurance is going to charge you more money as a result. Now, insurances don't just randomly make up dollar amounts to charge you. No, everything is based on mathematics and science. There's nothing random about insurance in general. That's probably the most mathematical, regular, real life job there is. Again, it's based on what's called actuarial science. But it's really this type of mathematics. Now, I'm overly simplifying it because I'm only giving you two possibilities here. In reality, there might be a whole slew of possibilities that I have to consider with different probabilities. But I want you guys to keep it simple, you know, a simple game of chance where I can win or I can lose with the following probabilities. Then I can calculate the expected return. It's actually pretty cool because if you went on and continued studying this type of stuff, the types of questions you can answer and the value you may be to some employer goes way, way up because you have the insight and you understand the mathematics to actually correctly describe the problem. So in most situations that we're going to look at, most situations, there's only going to be a couple of outcomes, you know, success, failure, here are the probabilities. Okay, so I'm going to stop there. Hold on.